Most great apes are lucky to reach 30, but humans, we regularly live into our 70s or 80s, nearly 3 times longer than our closest animal cousins, despite sharing 99% of our DNA. According to the basic rules of evolution, that shouldn't be possible. Evolution usually strips away anything that doesn't boost reproduction, so why do humans defy that logic? The answer might lie not in survival of the fittest, but in survival of the oldest. A secret hidden in a remote African community where grandmothers hold the key to our species' longevity. But what is so special about these elders, and why did evolution break its own rulebook for us? A chimpanzee born today in the wild faces a countdown clock that rarely ticks past 30 years. Even in the best protected sanctuaries, a chimp that reaches 50 is a statistical outlier, a kind of lottery winner among apes. Now put that next to the human experience. Across the globe, people routinely celebrate 70th, 80th, even 90th birthdays. In many countries, the most common age at death, what demographers call the modal lifespan, hovers around 75 or 80. This isn't just a modern phenomenon or the result of hospital care and pharmaceuticals. Anthropologists digging into the bones and records of hunter-gatherer societies find the same basic pattern. Humans who survive childhood often make it well into their 7th or even 8th decade. Meanwhile, among our closest relatives, the great apes, old age is a rare event. Most never live long enough to see their grandchildren, let alone their great-grandchildren. And yet, if you zoom in on the genetic code, humans and chimps are nearly identical. About 99% of our DNA is the same. The numbers don't add up. Evolution is supposed to weed out traits that don't help pass on genes, and yet here we are, a species built to outlast its own reproductive years by decades. Something in the human story bent the rules. The question is, what changed and why did it happen to us and not to them? Natural selection is a ruthless accountant. Every gene, every trait gets tallied by one simple metric. Does it help you leave more offspring? If a mutation helps you survive childhood, reach adulthood, or have more babies, it tends to stick around. But once reproduction slows or stops, the math changes. Evolution's rulebook says that traits which only benefit you after your last child shouldn't matter, because you're no longer passing on genes. This is why most mammals, from mice to elephants, show a steep drop in survival after their fertile years. In the wild, few animals live long enough to see their own grandchildren. The British statistician Ronald Fisher wrote about this in the 1930s. The force of natural selection fades with age, especially after reproduction ends. Biologists call this the selection gradient. The steeper the drop, the faster aging accelerates. There's also the disposable soma theory, which says bodies are built to last just long enough to reproduce, then maintenance falls off. Investing in long-term repairs doesn't pay off if you're not making more babies. In chimpanzees, for example, the end of fertility closely tracks the onset of rapid aging. Bones thin, teeth wear down, immune systems falter, and death usually follows within a decade. So the human pattern, decades of healthy life after reproduction, is an outlier, almost an evolutionary loophole. The question hangs in the air, why would nature ever let this happen? If evolution is so efficient, why are humans built to last so long after the job of passing on genes is done? Kristen Hawkes wasn't looking for a revolution in human evolution when she set up camp with the Hadza in northern Tanzania. She was just following the daily rhythm of life. Mothers with babies strapped to their backs, children darting through the brush, and, on the edge of the firelight, the grandmothers. What started as field notes soon turned into something bigger. Day after day, Hawkes watched as older women, long past childbearing, grabbed digging sticks and hiked out to the dry savanna. Tubers, starchy roots buried deep in the earth, became their specialty. On some days, grandmothers brought back more food than the mothers of young children. The numbers in Hawkes's journals told a different story than the textbooks. Children whose grandmothers were alive and foraging had a 25% better chance of surviving childhood. Mothers with a grandmother's help could have babies every 2 or 3 years instead of every 4 or 5. That's not just a small improvement, It's a total rewrite of the family calendar. Orphans and kids without grandmothers, meanwhile, struggled to get enough food, and their mothers faced longer gaps between births. The pattern was too strong to ignore. In the Hadza camps, an old woman's digging stick wasn't just a tool, it was the secret to more grandchildren, shorter birth intervals, and a thriving family. Hawke's fieldwork gave the first hard numbers to a radical idea. Maybe humans live so long because grandmothers made it possible. Not everyone in the field buys the grandmother hypothesis as the whole story. Michael Gervin, an anthropologist who has spent decades studying small-scale societies, points to late-life fatherhood as a possible driver. In places like the Tsimane of Bolivia, a surprising number of men father children well into their 50s and 60s, sometimes as much as 16% of men after age 60. The idea here is simple. If older men can still reproduce, evolution might keep the body running longer to support that possibility. This is called the patriarch hypothesis, and it's sparked plenty of debate. Others argue that what really matters isn't just who's making babies, but who's passing on knowledge. Elders often hold the keys to survival. How to find food in a drought, which plants heal wounds, or how to navigate social conflicts. The knowledge transfer model suggests that the brains of older adults, which remain metabolically active and sharp far longer than in other apes, are a big part of the equation. Meanwhile, molecular biologists are finding that the human aging clock ticks differently. Our bodies delay the onset of rapid aging rather than simply slowing it down. The field is crowded with competing theories, each backed by data, but nobody's got the final answer yet. Evidence for the power of elders shows up everywhere you look, sometimes in places you'd never expect. In the cool shadows of Shanida Cave, archaeologists found the bones of a Neanderthal man who had survived a decade with a crushed skull, a withered arm, and signs of blindness. He couldn't have hunted or gathered on his own, yet he lived for years, cared for by his group. The message in the bones is clear. Even in deep prehistory, old age could mean community value, not just decline. Fast forward to centuries-old Finnish parish records and you see the same pattern in the numbers. When a grandmother died suddenly, the odds of her grandchildren surviving the next year dropped by up to 15%. In the aftermath of disasters like the 2004 tsunami in Aceh, Indonesia, reports show that children in grandparent-led households weathered the chaos better than those without elders. These aren't just stories, they're data points from fossils, census books, and disaster logs, all pointing in the same direction. Whenever elders stick around, survival rates rise. The payoff isn't theoretical. It's written in the margins of history, in the bones of ancient relatives, and in the quiet resilience of families who've lost almost everything except each other. Inclusive fitness models flip the script on aging. In these simulations, every grandmother who sticks around and helps can tip the scales, not just for her children, but for her grandchildren's survival and her family's future size. The numbers are striking. In historical populations, daughters living near their mothers had more children, and those children were more likely to survive. Sometimes the difference added up to several extra grandchildren per grandmother. The effect grows in societies where food is unpredictable or raising young is more demanding, places where experience and steady hands matter most. This isn't just ancient history. Today, researchers track how communities with strong elder support weather disasters, adapt to change, and keep children healthy. As human health span stretches further, scientists are asking new questions. Could unlocking the secrets of elder resilience help everyone live not just longer, but better? The math says it's possible. Longevity, once an evolutionary puzzle, becomes a tool, a way for human groups to outlast, outthink, and outgrow their rivals. Humans routinely live 70 to 80 years, almost 3 times longer than wild chimpanzees, despite sharing 99% of our DNA. Field studies among the Hadza show that children with active grandmothers are 25% more likely to survive, and historical records from Finland reveal a sharp rise in child mortality after the loss of elders. While the grandmother hypothesis is strongly supported by demographic and archaeological data, questions remain about the precise molecular changes that set human aging apart from other apes. Fossil evidence like the Shanidar Neanderthal burial proves that care for elders has deep roots in our past. Today, as lifespans continue to rise, understanding the evolutionary role of older adults shapes public health and social policy worldwide. The evidence is clear: human longevity isn't an evolutionary mistake. It's a key to our survival, written in both our history and our genes.